Session with presentation by Fernando Quirós of University Autónoma de Madrid. We will speak about free boundaries and fractional filtration equations. Please.
Well, thanks a lot. First of all, I would like to thank the organizers of the program for inviting me to spend some weeks here in Cambridge. That's been a pleasure. And I would also like to thank the organizers of the conference for inviting me to give this lecture, this lecture. I would talk about recent work in trying to combine nonlinear diffusion and non-local diffusion. And well, this is something I did with my mentor and friend Juan Luis Vázquez, who is the chairman of this session, and with two other friends in Madrid, Arturo de Pablo and Ana Rodriguez. The kind of equations we are trying to understand is these equations, which are filtration equations, but instead of having here the Laplacian, we have a fractional power of it. So we will consider exponents between 0 and 2. I like writing it in this way so that sigma tells us the number of derivatives. And we will consider initial data in L1, and we will assume that they are non-negative, though the theory can be developed for signed data. As for the nonlinearities, they will be assumed to be continuous, non-decreasing, and we will fix phi at 0 equal to 0. So we have as examples, we have u to the m with m greater than 0. This is the fractional Porous medium equation. Log of 1 plus u. So here you have logarithmic diffusion. This is kind of the limit when n goes to 0. And also u minus 1 plus. So we would have the fractional Stefan one-phase problem. Okay. What is Pablo Sting already discussed this, but let me recall you what we mean by the by fractional power of the Laplacian. If for any non-negative self-adjoint linear operator, functional analysts define the fractional power in this way. Here you have the integral of the semigroup associated with A. So this is just the solution to this ordinary differential equation with initial data u. The A contains the boundary conditions in case there are any. Okay. So this is a generalization of this formula, which is true for positive numbers, and this makes sense if instead of putting here lambda, you put a non-negative self-adjoint linear operator. Okay. So in the case in which the operator A is the minus Laplacian, which is a positive operator, this is the formula. If you are in the whole space, I will restrict to this case, so things can be done in boundary domains. Then you can compute the Fourier transform of both sides, and it turns out that the Fourier transform of this side equals psi to the sigma times the Fourier transform of u. Okay. So this could have been taken as the definition of the operator, but and another you can also compute this singular integral, and you can compute its Fourier transform. Again, you get this. Well, if the functions are smooth enough. So if we write the operator in this way, it's quite clear that this is a non-local operator. The action on a function depends not only on the behavior of the function at the point, but also in the whole space. Okay. So why is it that we are trying to understand this? Well, this is a nonlinear, maybe the easiest. This is a nonlinear generalization of the fractional heat equation. This is also a non-local generalization of the filtration equation. Though this is not the only one, there are other ones. For example, there's a model that has been studied by Caffarelli, Vázquez, and some others, which has very different properties from the one we are studying. From the modeling point of view, these kind of equations appear in the hydrodynamic limit of zero-range processes. And let me also mention that in the case where phi of u is equal to the logarithm, if one does a certain Backlund transformation, one arrives to a problem, a non-local critical viscous transport equation, which is related to a certain problem related to the quasi-geostrophic equation studied by Córdoba, and Fontelos. Okay. So if the equation is linear, then things are very easy. One can write solutions in terms of the fundamental solution, the solution with an initial data delta function. In this case, you just can perform the Fourier transform, and the Fourier transform of the fundamental solution is explicit. It's got this form, and though only when sigma equals 1 and sigma equals 2, one has an explicit formula for P, for the fundamental solution, this expression allows to prove that the fundamental solution is self-similar, and this will play a role in the sequel. Okay. The properties of the profile of the fundamental solution are well known by now. It's regular, it's infinity, positive and regularly decreasing, and its decay at infinity is like one. It's like the power n plus sigma. And well, this function, this profile is only explicit when sigma equals 1 and sigma equals 2. Okay. Well, what happens in the nonlinear case? In the nonlinear case, we need to, well, things are not so easy, and we need to introduce a weak notion of solution, and then we would like to multiply by a test function and integrate by parts. What's integration by parts in this case? Well, if you multiply the Laplacian of a function by another function, well, you can pass to the, if they are smooth enough, you can pass to the Fourier side by Planck's formula. You can pass half of this power. You divide this into two parts. You group one half of it with the phi and the other one with the psi, and then you get this. And this suggests what the space should be. The right space should be the space that allows to do this integration by parts, and it's the homogeneous sublevel space H dot sigma over 2, which is just the completion of C infinity functions with compact support with this norm. Okay, well, here you just have the L2 norm of the Laplacian to the sigma over 4 of phi, or you can use this alternative form for the norm, which is the Gagliardo norm. Okay, and well, in this way we can define a weak notion of solution. Well, this I would call it an L1 energy solution, because we are looking for a function which is a curve in L1 such that phi of u is in the energy space, and well, here you multiply by a test function and integrate by parts, and this has to be satisfied everywhere, and then the initial data has to be taken in the L1 sense. Well, if the initial data are both in L1 and L infinity, then we proved that there exists a unique bounded weak solution. I will not go into the details because I want to talk about more recent work. Well, there's a tool that might be helpful, though it's not always needed, but it may simplify several things in some cases, and it's the sigma harmonic extension, which is something due to Luis Caffarelli and Luis Silvestri. And well, Pablo Sting already talked about this, so let me just remind it very briefly. The sigma harmonic extension is defined as follows. You have a function g, and then you compute a function which satisfies divergence of this power of y times the gradient of v equals 0 with boundary data. Well, you are adding. Okay, so I should explain this better. So you have your space here, Rn. You add a new variable y in this direction, and you study things in this upper half space. So you are constructing something which satisfies L sigma of v equals 0 here, where this operator L is defined here. Okay, and with boundary data at Rn given by g. And then if one computes, since Pablo explained this, I will not go into the details. If you compute the flux at the boundary, which is the limit as y goes to 0 of this power times the normal the derivative with respect to y of v, this is just minus a constant times the minus Laplacian to the sigma over 2. Okay, so this gives you a local realization of the problem, of the fractional Laplacian. You can compute things locally, which might be helpful.
Why is it like time in this case?
Well, yeah. Well, if you think about the case in which sigma equals 1, then you might think that this is time, and in fact you get the Poisson equation, the Poisson kernel. But why is not? It has nothing to do here with time. Nothing to do.
Yes.
So we can transform the problem into an equivalent local thing. We can pass from local to non-local in the following way. Given u, you compute phi of u, and you compute its extension. Let's call its extension w. And well, this allows you to pass from the non-local problem to the local one. And if you have a solution to a non-local problem, you can pass to the local one by taking the trace and then taking phi to the minus 1. And then, if we have my original non-local problem, the local problem in which it is transformed is the following. Phi of u, its extension is sigma harmonic, and then its normal derivative is just the minus Laplacian. Okay, but the minus Laplacian, if the equation is to be satisfied, should be equal to the time derivative of u. But u is just phi minus 1 of w, of the trace of w. Okay, and well, you need also the initial data, which are given by phi of f. Okay, so now you have a problem which is written just in terms of w. It's a problem in the upper half space, but now the equation lives at the boundary of the domain. Okay. And well, this kind of problems in which the normal derivative is given, depends on the time derivative. These kind of conditions are called dynamical boundary conditions, and there are several works on these kind of problems. And well, some proofs may be easier in this formulation. For example, existence. Though in the end, one may be able to do everything without using the extension. But sometimes it's easier to do this. Well, so up to now I just talked about existence for bounded initial data. What happens if you have unbounded initial data? Well, there's a smoothing effect if phi prime is big enough for large values of s. If phi prime is bigger than a certain power of s, like this one, then you and the initial data in L1 intersection LP with p greater than or equal than 1 and greater than a certain power, you need enough integrability, then you can control the L infinity norm of u in terms of the LP norm of f. And then by approximation you can construct solutions for more general initial data if they are in this space. And the proof just uses a Moser iteration technique. You have to use a regularization of a time regularization, because you don't know yet whether the solutions are smooth or not. And well, when you do Moser for the local problem, you at certain point, you have to compute the gradient of the gradient of the nonlinearity of the function. And here, you cannot compute this so easily. You have to substitute this computation by the so-called Strup-Baropoulos inequality, a generalized form of it. And then you have the fractional Laplacian of a function times the fractional Laplacian of v. And here you write this as the square of the fractional Laplacian of sigma over 4 of another function. And in this non-local case, you lose something. You have an inequality here instead of an equality. Okay, and the other ingredient in this Moser iteration is Sobolev's inequalities, and this we could also in this case we could also use Hardy-Littlewood Sobolev inequality if sigma is below the dimension, below n. But then for dimension n equals 1, you need something different. We use a Nash-Gagliardo-Nirenberg inequality. And the thing is that if you have a function which is in h dot sigma over 2, well, these functions are in this space, and you have some extra integrability, then you can control the function in a better space. Here you have a better response. Well, this works for any sigma below 2n, so we can apply this also in the case n equal 1. Well, so from now, well, up to now, what we have proved is that a function that is in L1 intersection LP for some p becomes immediately bounded. So the next step is proving that things are C alpha, and this was done by Athanasopoulos and Caffarelli by using the extension of Silvestre and Caffarelli. And well, in this case, you need a non-degeneracy condition on the nonlinearity, which is this 1. And the theorem says that you have a weak unbounded solution, a bounded weak solution, then U is C alpha in the set where U is between these values A and B, where you have the non-degeneracy condition, and you have that things are C alpha for some alpha. Okay. As particular cases, we have the non-degenerate case, phi prime greater or equal than C, strictly positive. Then things are C alpha everywhere. Also, the porous medium case for m greater or equal than 1. The fast diffusion case with m between 0 and 1, but well, in this case, you cannot allow U to cross to touch the level 0. So in order to have that the function is continuous everywhere, you need positivity. And well, you have to prove positivity without knowing a priori that the solution is continuous, and that takes a while. Okay, and as for Stefan, you will have a C alpha continuity in the set where U is above 1, but not in the set where U is below 1. And anyway, in this same paper, Athanasopoulos and Caffarelli show that the solution is continuous, but only continuous. They are not able to prove that it's C alpha continuous. Okay, so now we would like to prove that, and this is very recent work, that if the solution is C alpha, then it's classical. So I will only explain the main ideas, and the idea is the following. We write the equation, well, we write the equation as a perturbation of a linear equation. So let's think about a point x naught t naught, and we need the solution. Well, we need the equation not to be degenerate there. Okay, so we need phi prime to be strictly positive at U naught. Okay. So now I just write a linear equation. Well, I have here a constant, and here I pass the nonlinearity to this side, and here I have what I have added. And well, since the fractional Laplacian of a constant is 0, then I can add these constants here, this 1 and this 1 here. Okay. And here what I have is the original nonlinearity minus the first two terms in Taylor expansion. So I have something which is quadratic. Okay. So the two key points is that the first thing is that by studying the linear equation with the right-hand side, which is the fractional Laplacian of something, we see that U is as regular as what we have here on the right-hand side. And the second point is that f of U is more regular at the point x naught t naught than U. If it was at the point, if it was C alpha, it will be C2 alpha. Okay. Well, one has to be more precise when doing these things carefully. And while this idea of doubling regularity was used by Caffarelli and Basser for the quasi-geostrophic equation, but in the case sigma equals 1, then the kernel, the fractional heat kernel is explicit, and in their case the right hand side is local. Instead of having here the fractional Laplacian, they have a gradient, and things are easier also in that sense. And well, we apply these ideas first in the case of logarithmic diffusion for the critical case n equals sigma equals 1. Again, sigma equals 1, that's easier. So let me explain the main ideas. One has to study the linear problem with the right-hand side, which is not a standard. It's the fractional Laplacian of a function g. So one uses a representation formula. So you write the solution in terms of a convolution with the convolution of the kernel, the fractional Higgs kernel with initial data, and then you have something which takes account of the right-hand side. Okay. Well, you pass. Well, this is formal. You have to be careful with all these things. You pass the operator, you integrate by parts, and you pass this to the Higgs kernel. And then you have here. Well, this part is smooth because P is smooth. So you have to know what's the smoothness of this part here. And you have the convolution of G, which is the alpha against something, which is the fractional Laplacian of P. Okay. So the main difficulty is that the kernel A, well, one of the main difficulties is that the kernel A is not explicit. However, you know what its Fourier transform is. It's this one, okay? And then it's self-similar, okay? Well, one has to use the topology adapted to this problem. In this case, this will depend on sigma, which tells you which is the relation between time and space. And well, this topology, well, this distance is self-similar also, and you have to use sigma parabolic spaces. Okay, so let me tell you that the main ingredients in the proof are the fact that we have estimates for the kernels, even when we don't know them explicitly, and they come. These estimates come from the self-similar form that the kernel has, and for its derivatives. And well, this turns out to be the critical exponent for integrability after the change of variables. So we have a singular kernel there, and then you need to have some cancellation and well, in fact, you have cancellation, but you don't have cancellation in balls. You have certain cancellation in sigma balls. So you have a kind of ellipses that have to do with the value of sigma. And well, of course, you have to divide things into regions close to the singularity, away from the singularity, and all these things. And what you get in the end is that if U is a bounded weak solution and phi is C1 gamma with 1 plus gamma greater than sigma, okay, it has to be differentiable enough to apply to it the fractional Laplacian, and phi prime is positive, then U is a classical solution. And well, there's a local version of this theorem that allows to deal also with degenerate problems as the porous medium equation. But then you need to know a priori that the solutions are positive, okay, to be sure that phi prime is positive. Okay. And well, you can obtain further regularity if phi is more regular. In fact, you will get, if phi is ck gamma, then the solution will be ck alpha for some alpha. Okay. Well, let me tell you something. This cannot be applied to the porous medium equation. In principle, what you do here is you obtain an equation for the derivative, and you apply the previous theorem. But you don't know that the derivative from the first theorem. You don't know that the derivatives are bounded, so you cannot apply the second one, because this is only for bounded solutions. So since this is a conference on free boundaries, let me explain you first that there's no free boundary, and then that there's one. The first thing is that, well, let me explain that for all these problems you have positivity. If the initial data are non-negative, then the solution is non-negative. This is just a comparison argument. But then, well, a formal computation which can be made rigorous shows the following. Imagine that at the point you touch 0 and that the solution is not identically 0 there. Well, there are cases in which you have extinction at finite time, so it may happen that solution becomes identically 0 at the point. But in case this does not happen, well, since U satisfies the equation, the time derivative at the touching point, at the point where the solution touches 0, is equal to this fractional Laplacian of phi of U. Then you compute it with the formula. Since U is 0 and phi of 0 is 0, you just get this, and this is positive. If U is not 0, And well, I am saying this. Yeah, that's it. Yeah. So things become positive. What happens? Anyway, I will show that if there's a distinguished value in the nonlinearity or somewhere, then there will be free boundaries. So let me talk, for example, about the fractional one-phase Stefan problem. In this case, we have this equation with the nonlinearity, which is 1 minus 1 plus. Okay. So in this case, U stands for the enthalpy, and well, U minus 1 plus in the local problem stands for the temperature. Well, we know that U will become positive immediately. But what about the temperature? U cannot be positive everywhere, because where theta is positive, U has to be above the level 1, okay? And U is integrable, so the places where theta is positive cannot, the measure of the set where theta is positive cannot exceed the L1 norm of U, okay? So there will certainly be a free boundary. And well, in the same way, you can prove that there will be, well, imagine that, that there will be localization. I mean, this restriction, you have this restriction all the time, so the positivity set for theta will not, we'll have finite measure all the time, okay? There's a restriction for that. This happens also for the local problem. So there are open problems in this case. One of them is the regularity. Well, one knows that U is smooth, is continuous, but not more than that. U is C alpha in the inside, and in fact, the local version will allow to show that that U is classical where U is above 1, where theta is positive, but one doesn't know what's the regularity up to the free boundary, or across it, and one does not know what's the regularity of the free boundary. Okay. Another question is how to pose this as a classical free boundary problem, because here it's not clear what the flux is. So what's the rule that prescribes the velocity of the free boundary in terms of some quantity related to theta? And let me talk about the last free boundary problem here, and it's a Mesa problem. Well, here we consider the nonlinearity U to the m, and if you let m go to infinity, formally you get that phi of U equals 0 and U is between 0 and 1, and when U equals 1, phi of U can take any value between 0 and infinity, okay? And you cannot take the any values above 1. So, well, like in the local case, m equals 2, one can prove, well, this is work in progress with Juan Luis, that that for any positive t, um will converge to something which does not depend on t. It will converge to a function f tilde, which is f minus the minus Laplacian to the sigma over 2 of a function w. The convergence is in L1, uniformly in t, where w is a solution of this obstacle problem posed in the whole space. Okay. So w and its fractional Laplacian belong to L1. W has to be above the obstacle, which is 0, and then you have this here. This is telling you that the limit f tilde is always below 1, is less or equal than 1, and you have a dichotomy. Either w is positive, well, if w is positive, then f tilde equals 1, the limit equals 1. If w is 0, then you don't have any restriction on this. Well, the proof uses strongly the Biocchi variable, which is just the integral in time of this power. Okay, I'm not going into the details because I'm running, well, I ran out of time, so this is just the last slide. The thing is that well, one can see in the equation in the equation for W that if the L infinity norm of f is less or equal than 1, then this projection onto a mesa of the initial data does not take place. I mean, the projected solution, the projected f, coincides with f. Okay, so this is interesting. For example, if you have an f which is compactly supported for the original problems with m not infinity, the solution becomes instantaneously positive. However, in the limit, you get something which is still strictly, well, which has compact support. Finally, if W is above 0, then the F tilde will be equal to 1, that I already said. And then, well, one can prove that the mass is conserved in this projection, so F tilde has the same mass as F. And this tells you, well, this is my last comment, that W will be compactly supported. Why is this? Because if in places where W is greater than 0, the F tilde will be equal to 1, and the total mass of F cannot exceed the total mass of F tilde cannot exceed the total mass of F. So this tells you that W is compactly supported, though F tilde is not, because the fractional Laplacian of something which has compact support which has a tail. So the limit U will have a tail, but the limit W will not have a tail. Okay? And well, I will skip this, so I'll stop here. Thanks for your attention.
So I have one question. So for the boundedness, you use the non-local formulation, as far as I understood.
You can do it. Well, you can do it in the local formulation or in the non-local one.
Right.
In the first time we did it with the local formulation, but you don't need it.
But for C alpha, you can do it in both?
You can do it in both. In the original paper by Atanasopoulos and Caffarelli, they did it using the local formulation.
Okay.
But then there's a subsequent paper by...
So you can go all the way to classical solutions in both frameworks?
Classical we did just in the non-local formulation.
Okay.
We didn't need to go upstairs.
So there is hope if you have operators that do not have this extension property, that there is hope that you could actually run the test.
Yeah, there is a hope. There's a
This is one of the main ideas of Luis Caffarelli years ago, was that even if the extension allows you to do many things and have intuition about what to prove, then it's interesting to do the proofs using integrals and harmonic analysis, because you don't have extensions all the time.
You don't have, for example, if instead of having this very precise kernel, you have something that has a singularity like the fractional Laplacian, but it's not, then you don't have an extension. But well, going up to C alpha, you can do it. In fact, this was done by Caffarelli, Chan, and Basser. But proving that things are classical is not that easy. The problem is that, well, you still have bounds for the kernels, but you don't have this cancellation property, which depends very much on self-similarity.
So either you know the extensions or you know very well the kernels.
Yeah.
One of both.
Yeah.
My question about this parameter sigma, which creates fractional derivative. You consider that it is between 0 and 2, just less than 1 this power. But generally speaking, fractional derivative will be for greater than 2 sigma. You may have over 2, 5 over 2. My question, all this technique will still work?
Well, no.
If there is no maximum principle.
There's no maximum principle, then things are much more difficult.
But still you can characterize using an extension in that way. I mean, you can characterize Laplacian to the 5/3.
No, that's you explained that the other day, but
normal calculus is true. The analysis of equations, nonlinear equations, is not true because they use maximum principle. You have to do it by using
another technique.
So nonlinear equations will not, in principle, be true. Anything of what we say. You have to, if you want to results, you can prove. You have to prove it again.
Just a question, because, for example, thin film equation is for order, so to involve.
In fact, we are thinking about interpolating up to the thin film equation, and it's very interesting. But it has to use other techniques.
Yeah, you lose maximum principle, then a lot of things do not work. But some other things might work. Yeah.
Very interesting question, right?
Yeah.
Okay.